Good evening. Can you hear me?
Good evening, sir. Yes, sir.
Okay.
Good evening, sir.
Let us wait for a couple of minutes if some more students join. Maybe some may not join also. After 2 minutes, we will start. Any question regarding this previous material? What we are discussing? We are still going about this turbojet engine and different aspects. What are the different aspects as compared to industrial gas turbines? So diffuser we have seen, and nozzle also we have studied briefly. One like how to analyze, and then we were going about through some of the important performance metrics or parameters to calculate or to quantify the performance of jet engines. And we have started with propulsive efficiency, okay, because this type of parameters were not defined or cannot be defined for industrial gas turbines. These are new and only applicable for jet engines. So that's why we are focusing on these things. So let us continue our discussion from the previous class onward. I hope you can see the screen. Can somebody confirm?
Yes, sir.
Okay, recording has started. So propulsive efficiency to already last 2 days we are just stuck here. So I guess you already understood what is propulsive efficiency. If there is any question you can ask me. Okay. So again, just to summarize in one line, it gives us an idea about how much of the uh, uh, propulsive thrust, how much of the energy or kinetic energy that is generated for the exhaust gases by the engine is used for propelling the aircraft forward, and how much of it is getting lost to the atmosphere. Okay, so the kinetic energy that is contained in the uh, exhaust gases, part of it is used for propulsive thrust, which is for using or propelling the aircraft forward, for moving the aircraft forward, and rest of it gets lost in the atmosphere. So the part which is used for moving the aircraft forward can be calculated based on the thrust and the velocity, F into Vi. Vi is the velocity of the aircraft, F is the thrust, and rest of it which is lost in the atmosphere is the kinetic energy of the gases, exhaust gases, from an absolute standpoint. So if I am standing on the ground, I can see that the exhaust gases leaves with a velocity Ve minus Vi. So for that the kinetic energy is half m dot I V minus Vi square. That kinetic energy from the absolute reference point is not used. That is the velocity of the gases that is just getting dissipated in the atmosphere. So that is lost. So this is our propulsive efficiency, and we have seen the different types of aircraft that we have discussed in detail, the different types of aircraft and why different types of aircrafts have different types of engine. Military aircrafts, civilian aircrafts, low speed civilian aircrafts, high speed civilian aircrafts, why they have different types of engine, and that is because propulsive efficiency should be high for all types of aircraft, and the propulsive efficiency depends on the exhaust gas velocity, and exhaust velocity depends on the type of engine. Turbojet engines have highest exhaust gas velocity, turboprops have lowest exhaust velocity. There is no exhaust velocity per se, but lowest velocity of the air which is pushed by the propeller, and turbofans have in between velocity. Accordingly, their aircraft velocity also changes. The other performance parameter you are already familiar with. Okay, the second important parameter for quantifying the effect or for quantifying the efficiency of jet engines is known as thermal efficiency. It is defined as the ratio of the propulsive power that is generated by the energy that is contained in the fuel. Okay. So denominator is very familiar to you. Denominator is the mass flow rate of fuel m dot f into calorific value of the fuel, energy per kg of the fuel. So mass flow rate into energy per kg of the fuel gives us energy per second or per unit time released by the fuel, or what is contained in the fuel used up per second. Okay. And propulsive power is the power that is being generated when you consider how much is the change in kinetic energy of the gases when it passes through the engine. So what is the initial kinetic energy of the gases when it enters the engine? Initial kinetic energy is half m dot I Vi square. M dot I is the mass flow rate of air and Vi is the velocity of the incoming air relative to the engine. Remember, this is relative to the engine. Okay. So we are thinking in terms of from the perspective of the engine. You are sitting on the engine, you see that the air velocity is Vi. Okay. For a person who is standing on ground, the air does not have any velocity at the inlet. It is the engine which is moving forward at Vi velocity. But relative to the engine, we have to calculate the thermal efficiency, because from the point of view of the engine, we should know how much the air is accelerated. Okay. So air comes in at Vi velocity. So the inlet kinetic energy is half m dot I Vi square. What is the exit kinetic energy from the engine? So the exit mass flow rate has increased. Now the new mass flow rate is m dot I plus m dot f. So I can write this as m dot I into 1 plus f. Okay, half m dot I 1 plus f. And the exit velocity is v. That is how we are denoting. So half m dot I 1 plus f v square. Okay. So this divided by m dot f, which we can write as m dot I into f. Okay. So this is our definition of thermal efficiency. If you can ignore the fuel air ratio as a very small quantity, around 2% error will be there. If we ignore this, we should not ignore this when actually solving the problems. But for simple derivations like this, we can ignore this just to check or to simplify the equation. But in actual problems, we should not ignore this, because it will lead to around 2% error. Okay. So if you ignore this, we can write this as so 1 plus f can be written as 1. So m dot I cancels, and we are left with half V square minus Vi square by f into QCV. Okay. So this is the thermal efficiency. This denotes how efficiently we are converting the energy in the fuel into the kinetic energy of the exhaust gases. Okay. Then this is the first part of the energy conversion. This actually gives us the energy conversion in the engine. And then how much is the kinetic energy that is generated, and how much of it can be used for actually propelling the aircraft forward outside the engine, that occurs, that is the second part of the conversion of energy, and that is given by the propulsive efficiency. Okay. So these two are different. So you can say that first the energy of the fuel is converted to kinetic energy, that is taken care of by thermal efficiency, and then that kinetic energy is, some part of it is converted to thrust power, that is taken care of by the propulsive efficiency. Okay. So the overall efficiency can be defined as a multiplication or as a product of this propulsive efficiency and the thermal efficiency. Okay. And what is its significance? It denotes the thrust power. So this numerator, thrust power. So useful propulsive energy, not the total propulsive energy, useful propulsive energy, the energy that is used for propelling the aircraft forward. Okay. Which we have defined as F into Vi. So let me just keep this also open here, so that you have that as reference. Okay. So PT, F into Vi. Okay. Divided by the total calorific value of the fuel. So PT by total calorific value of the fuel is equal to the propulsive efficiency into the thermal efficiency. So now one question can come to your mind is that if we write it like this, whether this is actually equal to eta P into eta thermal, because we are seeing from the equation that these two equations are different. This can only be equal, this PT by m dot f QCV can only be equal if this propulsive power, this numerator, is equal to the denominator here. Okay. See, PT by propulsive power into propulsive power by m dot f QCV should give you PT by m dot f QCV. So it means that whatever I am writing here as propulsive power should be equal to this denominator here. Here we have defined propulsive power as, if you ignore fuel air ratio, the propulsive power as half m dot I v square minus vi square. Okay, here the m dot I got cancelled, but the propulsive power is half m dot I v square minus vi square. Okay, which is different from this form that we have written here, f into vi plus half m dot I v minus vi whole square. So it means that these two should be equal, and we can check that they are equal actually. So how can we check? So say we sum up the thrust power plus unused kinetic energy. This denominator, let us sum up. So thrust power is F into Vi, and unused kinetic energy is half m dot I V minus Vi square. Okay, this denominator here. So F, what is F? By definition, F is equal to, if you ignore fuel air ratio, m dot I V minus Vi. Okay, m dot I V minus Vi. We are ignoring the fuel air ratio here for this calculation. Let me keep it open. So F is m dot I V minus Vi, and one more Vi was there. So this plus half m dot I V minus Vi whole square. Okay. So if you take m dot I V minus Vi common, you are left with Vi plus half V minus Vi, which is equal to half V plus half Vi. Okay, if you add these two terms. So ultimately you get half m dot I V square minus Vi square. Okay. So this term is actually nothing but equal to this propulsive power, half m dot I V square minus Vi square. So we can check that the denominator here is nothing but equal to the numerator of this thermal efficiency. Denominator of this propulsive efficiency is equal to the numerator of the thermal efficiency. Okay. So basically overall efficiency is thermal efficiency into propulsive efficiency. Any questions on this? Is this clear? This should be very clear to you. This is somewhat confusing to every year to the students. Any questions on this? This is very easy to understand if you consider that the energy conversion is occurring in two parts. First, there is some chemical energy in the fuel itself, which we can consider as m dot f into QCV. In the engine itself, this energy gets converted into two parts. One part is used in the turbine to generate work, which runs the compressor, and rest of it is used for increasing the kinetic energy. Okay. So the work of the engine is to convert the, so ultimately when we see the efficiency of the engine, we see how efficiently the fuel energy has been converted to kinetic energy of the, to increase the kinetic energy of the exhaust gases. Okay. Now the second part is that how effectively this additional kinetic energy that was generated, how effectively that is being used by the engine for moving forward. Because we know that all of the energy is not used. Some of it is getting dissipated, which is getting lost to the atmosphere. And it is getting effectively used only if the velocity of the aircraft is near to the exhaust velocity. Okay. So this is the second part. So overall efficiency of the aircraft propulsion can be defined as propulsive efficiency into thermal efficiency. Okay. Any questions? Otherwise, we are just going to move forward. No questions, I assume. So if you just take a look back at what we had discussed in the turbojet part, let me just open the diagram. So for the turbojet engine, we had the diffuser part, and we have taken a look at how to calculate the efficiency from the efficiency of the diffuser, the temperature, or the other way around. If the temperature is known, how to calculate the diffuser efficiency. We have defined two types of diffuser efficiency: the ram efficiency and the isentropic efficiency. Then the compressor, combustion chamber, and turbine part you already know, but I have again revised here. You can go through the notes how to calculate. And for the nozzle also, we have seen how to calculate the exhaust gas velocity from the nozzle based on the enthalpy difference, means a change in enthalpy that is occurring. Okay, it should be there in the notes. How to calculate the aircraft means exhaust gas velocity based on nozzle efficiency and other parameters. And then from that, how to calculate the thrust developed. Okay, and then we were discussing about all these parameters. Now, this discussion on nozzles is actually, at that time I did not mention to avoid confusion, but this is only valid for convergent nozzles which are not in choked condition. Okay, if the nozzle is in choked condition, then this whatever we have discussed here is not valid. Okay, why it is not valid? I think we had a discussion. If the nozzle is not in choked condition, the exhaust gas will, I think we have discussed this. Okay, again we will just repeat it. Somewhere it must be written in the old discussions. But we will discuss again, so don't worry. Yes, so if you can go back to the recorded lectures, you will be able to see. I will upload the lectures. If the nozzle is not at choked condition, so I will just quickly again summarize once, because this is the confusing part where everybody gets confused. So say you have a nozzle like this, convergent nozzles. We are only considering convergent nozzle because these are the only common type of nozzle in aircraft engine. Why these are the common type? I will also discuss that. Okay. But let us consider convergent nozzle where the inlet velocity is very small, almost negligible, or certain velocity is there, but not very high. Okay. This inlet velocity is the exit velocity from the turbine, previous turbine stage, and the flow is accelerated here. Okay. So say the inlet pressure is Pi and the exit pressure is outside atmospheric pressure is Pa, ambient pressure is Pa. Okay. So what will be the pressure at the exit of the nozzle? Initially, it will also be equal to Pa. Now, if the ambient pressure is lowered, means say if you can somehow control the ambient pressure or the altitude is changing, ambient pressure is lowered. Okay, if you are going to higher altitude, ambient pressure is lower. So what happens? Well, let us put some numbers. Say here the pressure is 100 kPa itself, and say ambient pressure also was 100 kPa. So no flow will occur. Now you are reducing the pressure. If it is at 90 kPa, there is a pressure difference from this side to this side, and flow will occur. If it becomes 80 kPa, because the pressure difference is now higher on this within the nozzle, flow rate should increase. This will keep on going until what point? We have discussed this. Can somebody say at what point?
Choked pressure, sir.
What pressure?
At
Choke pressure, critical pressure. Okay, choke pressure you are saying. Critical pressure. So critical pressure ratio, there is a critical pressure ratio, P star by P naught, which is given by 0.588 or something like that we had calculated. I don't remember. So you can check this value. I think we have the value written also in the
0.528, sir,
note.
actually.
What was it?
0.528.
0.528. Have I calculated here somewhere? We have not. I have just given it as an exercise. Okay. Whatever is the value. Okay, you just check this. So 0.5 something. Okay. So at that point, so this P naught is, you can calculate this P naught at the P naught is half rho V square, or you can calculate from Pi square, or you can calculate from the temperature. T naught by Ti, sorry, T naught is equal to Ti plus half Vi square by Cp, means Vi square by 2 Cp. So you know the iso of this stagnation temperature. So if we assume an isentropic nozzle, the stagnation temperature does not change. Even if this nozzle is adiabatic, the stagnation temperature does not change. So stagnation temperature remains constant even at this point also. So at this point, stagnation, if it is an isentropic nozzle, the stagnation pressure also remains constant. And stagnation pressure is given by P naught by Pi is equal to T naught by Ti to the power gamma by gamma minus 1. So P naught we already know from the inlet condition. So we know we can find out what should be the P star. So say in this case, if it is P naught is 100, if the inlet velocity is negligible, at 52 kPa we reach sonic speed at this point. And beyond this point, even if we keep on decreasing, if the pressure becomes 20 kPa, the velocity cannot change. It will remain as sonic speed. So what will be the pressure at this point at that moment? If outside ambient pressure is 20 kPa, still the pressure at this point should be equal to the critical pressure. If it is 52 kPa, it will remain as 52 kPa. Okay, I think we had calculated once. Let us check that value. Point 0.5833. This is for air. Okay, 0.5833. For gamma G, I don't know whether this calculation is correct or not. You have to check. Similarly, you can calculate for gases also. Okay. So this only depends on the gamma value. So once you reach that, this P should become unequal to P outside pressure. Okay. So there will be a, so if I see the pressure in the nozzle, it will follow a variation like this. So this diagram is not accurate, but so this is pressure and this is the x direction of the nozzle. So pressure will follow some path like this. So it will decrease, and this is say the inlet, and this is the critical pressure P star, and this is Pi, and then there will be a jump, and outside pressure will be the ambient pressure. There will be a sudden jump outside, and there will be an ambient pressure. So in choked condition, if it is an isentropic nozzle, then it is not difficult to calculate the pressure and other conditions. But if there is losses in the nozzle, if the nozzle is non-isentropic, then it becomes tricky to calculate what is the exit pressure. Then the exit pressure is not equal to whatever is the critical pressure for a isentropic nozzle. Okay, the exit pressure actually is different. So we want to find out what is the exit pressure. That is very important for us to calculate. Okay, so we want to find out what should be the exit pressure. So we want to study about convergent nozzle at choked condition. Why this exit pressure is important for us? Can anyone say, based on the couple of previous days discussions? Why is it needed for us? Say if we know the temperature, exit temperature, we should be able to calculate from the temperature difference in the nozzle the exit velocity, exhaust velocity. Then what is the requirement of knowing the exit pressure? can you use some logical thinking or logical connection to find out that exit pressure plays a very important role in the performance parameter? No answer?
Sir, calculation of pressure thrust.
Calculation of
Pressure thrust.
let us look at when we calculate what process we follow for thrust calculation. I have shown all these steps in few classes back. So first we start with the diffuser step by step. So diffuser inlet conditions are known to us. Then based on the diffuser efficiency, we calculate what is the inlet condition to the compressor. By inlet condition, we mean that inlet pressure and inlet temperature. Then from the inlet pressure and temperature in the compressor, we calculate what is the exit pressure and temperature of the compressor. Okay. Then we already have the exit temperature from the combustion chamber known, because that is the maximum temperature of the cycle. And pressure also is known based on whether there are any pressure losses or not. So only thing in the combustion chamber that we calculate is fuel air ratio. Once the fuel air ratio is known, from the turbine part, based on the turbine efficiency, we actually calculate by equating the turbine work to the compressor work, we calculate what is the turbine exhaust temperature, actual temperature. Why we calculate the actual temperature? Because that is what only we can calculate. So then using the efficiency of the turbine from the actual temperature, we calculate the ideal temperature, isentropic temperature. And based on the isentropic temperature, we calculate the exhaust pressure of the turbine, because our relations are only true for isentropic processes, means pressure ratio is equal to temperature ratio to the power gamma by gamma minus 1. This only we can apply for isentropic process. That's why we need to calculate the isentropic temperature so that we can calculate the exit pressure. So exit pressure from the turbine is known and the exit temperature is known. So inlet condition to the nozzle is known. Now if the nozzle is not choked, the exit pressure is also known. So based on the inlet and exit pressure, we can always calculate what is the temperature ratio across the nozzle based on the pressure ratio. And once you calculate the temperature ratio, already inlet temperature was known. So exit temperature we can find out. So based on the difference in temperature, you can find out what is the change in enthalpy and what is the exit velocity. Then based on the exit velocity, you can find out the thrust that is generated. So that was our ultimate aim, to find the thrust, and we can calculate the thrust. So what happens when this nozzle is choked? So what will be the, where will be this 0.5? Will this be P5 will become equal to PA, or will it be higher than PA or lower than PA? P5 is the nozzle exit pressure.
Higher, sir. It will be higher if nozzle is choked.
Yes, correct. So it is higher than PA. Okay. So if it is higher than PA, I guess best option is that whatever you had suggested few classes back, to open it using this Microsoft. Edge, so that I can draw there itself. This one, right? So if it is higher, say if it is, it's not accurate, but anyway, you can imagine. So say this is P5. Okay, it's very difficult to write using the mouse. Say this is P5 pressure, and this is the temperature. Okay. So critical temperature we can already calculate based on the inlet temperature, correct? Because temperature ratio is fixed. So what will be the temperature ratio? Does anyone know? Or how can we calculate based on previous class notes? For calculating the diffuser, we have derived one equation like this. I am just jumping forward and backward. but it should be clear to you. We have derived one equation like this: T0A by TA is equal to 1 plus gamma minus 1 by 2 m square. So if the nozzle is in choked condition, at that point, what is the Mach number at the exit of the nozzle?
1.
So then what is the ratio between the stagnation and static temperature?
Gamma plus 1 by 2.
Gamma plus 1 by 2. Now the stagnation temperature, can it change in the nozzle, in an adiabatic nozzle? Can the stagnation temperature change if there is no heat loss?
No.
It cannot
No, sir.
change because there is no heat loss. The enthalpy also cannot change, and as a result, Cp into T also cannot change. Stagnation means total enthalpy. Stagnation enthalpy cannot change in a nozzle. That is the, from first law itself you can find the stagnation enthalpy is constant in a nozzle. Okay, if you remember the first law, you should remember this. That what is this? These things are so awkward. Q plus HI plus half VI square, where VI is the inlet velocity, is equal to W plus HE plus half V square. This is the first law for steady state steady flow process, ignoring change in potential energy. You have read in thermodynamics. If there is no heat loss, and obviously nozzle cannot do any work because there is no moving part. So this is nothing but equal to H0I, inlet stagnation enthalpy, and this is H0E, outlet stagnation enthalpy, or at any point in the nozzle. So at any point in the nozzle, H0 should remain equal because it cannot change. The sum of static enthalpy and kinetic energy will remain constant. Okay. So stagnation enthalpy cannot change, stagnation temperature also cannot change. So it means that stagnation and temperature is same. So what should be the stagnation temperature if the inlet velocity is almost equal to 0? Stagnation temperature will be equal to, even if it is certain velocity, stagnation temperature only we are directly calculating, right? It is T04. We have calculated at this point from the turbine outlet condition. So this is already known to us, T04. So what should be T star at this point? What is the stagnation temperature at this point? After the
Same,
expansion
sir.
in the nozzle? Same, right? So it is the same temperature equal to T04. So already temperature is known here. Okay, stagnation temperature is known, and static temperature, is it known at this point? I will come to formally discuss these things, but I just want to see how your thought process means, how you guys are thinking. But we will discuss these things properly, step by step. So you don't have to worry that these are not in the notes. Everything is there. But I am just trying to see how you are thinking. So at 0.5, stagnation temperature is still equal to, if it is in choked condition, is equal to T04. What do we have any information about the static temperature at this point? Sanjay, are you there? Sanjay? I
We
cannot
don't have
hear
any
you.
information, sir.
Velocity you have to find.
Is this Ujjwal? Whose voice is it?
Yes, sir. Yes, sir.
Suman.
Suman or Ujjwal?
Sir. So actually,
Ujjwal,
sir,
sir.
velocity we have to find, sir, to find the static.
We don't have any information about static temperature at this point, even if it is choked condition.
Sir, if it is choked, then we have.
It is choked. That's why this pressure is high. If it is not choked, we will be at this point, right? Only if it is choked, then only can P5 be higher than PA, right? Otherwise, how can P5 be higher than PA? Is it possible that if it is not choked, P5 is higher than PA. It cannot be possible. So only if it is choked, P5 is higher than PA. Means there is a discrepancy between the atmospheric pressure and the exit pressure, or a jump is there. Somebody has written something, or mic does not work properly, sir. For Sanjay or for me? Whose mic is not working? Okay, fine. So it is a choked condition. When I am drawing P5 like this, it means that it is a choked condition. So if it is choked condition, what is the static temperature? Now do we have any information?
Critical temperature.
It is the critical temperature, and how can we calculate it?
Like you have the equation on the left side.
What is the equation? We have this equation. Say if I write here, we know that the T05 is equal to T04. Stagnation temperature is same. So T05 by T5. T5 is the critical temperature, right? If it is choked. So this is equal to 1 plus gamma minus 1 by 2 into m square. M is 1 square. So gamma plus 1 by 2. So gamma we know already. If it is gas, so gamma of gas. Okay. So from this, we can always find what is T5, right? Static temperature we can find at this point. Is it clear to everyone how we can find the static temperature in this point? We will come to this discussion again, but from this discussion, is it clear how we can find the static temperature at this point? If it is choked, nozzle is choked. Or is there any confusion? Let me again repeat. So there can be only two things, right? Either the nozzle is choked or it is not choked. If you are given a problem, there can be only two things that can happen. Either the nozzle is choked in a convergent nozzle or it is not choked. If the nozzle is, and say you know the inlet conditions from previous calculation, the inlet temperature and pressure is known and the ambient pressure is known to you. Now, if the nozzle is not choked, okay, let us first consider the condition when the nozzle is not choked. How will you find the nozzle exit conditions? Tell me. If the nozzle is not choked, how will you find the nozzle exit condition? What are the steps required? And one of you can tell. Ujjwal?
Sir, like the exit pressure will be the atmospheric pressure.
Correct.
So
Then
we have the pressure ratio. Using that, we can find.
we will find what point using the pressure ratio. Nozzle efficiency is given to you.
So 5A we can find static temperature at 5A.
5S is isentropic point. Static temperature at 5S we will find. And then from the using the nozzle efficiency, we will find the temperature at 5. Okay.
Yes, sir.
And now how will you calculate the velocity, exit velocity based on this temperature difference? T04 minus T5. Okay. Assuming that at T0 means at this point the velocity was negligible. If the velocity at this point is given, obviously you can find T4 static temperature also. Then also you can find the velocity, but otherwise you can. So that is the case. For that is easy to find if the nozzle is not choked. If the nozzle is choked, how will you find the exit velocity at this point? And how will you find the exit conditions? Now we are coming to today's discussion.
Sir, Mach number is 1, so we can get the exit velocity.
Mach number is 1, we can get the exit velocity. How will you get the exit velocity? If Mach number is 1, what is the equation of exit velocity? Root over gamma at T. What happened? Am I audible?
Yes, sir.
So if Mach number is 1, how will you get the exit velocity?
No, sir, we need the temperature.
We need the temperature. So what will be the steps in calculating the exit velocity?
We first
Has already
find out the
told.
temperature.
I am just repeating again so that
Yes, sir,
everyone
from the
understands.
From the equation you wrote in the left side.
Yes, stagnation temperature. If m is equal to 1, the ratio of stagnation to static temperature is gamma plus 1 by 2. This is a very important relation. Okay, this we will discuss this, but this thing you should always remember, that T0 by T star is equal to gamma plus 1 by 2. Okay, so from that we can find the static temperature here, and from the static temperature we can find the velocity here, gamma r into T star root over that. Okay, so we can find the velocity. So now my question was, initial question, if you remember 20 minutes back, why do we need the pressure? Because we have already found the velocity. So what is the need of, I asked you, what is the need of finding the exit pressure P5? Whether there is any need of finding the pressure, or we are happy with finding the exit velocity itself.
So like we should know whether the nozzle is choked or unchoked.
That is one very good point. Without doing that calculation, actually you cannot know whether the nozzle is choked or not. Okay, so you have to start with the assumption first to find the critical pressure, critical temperature and pressure, and check whether it is choked or not. If it is choked, then you have to do a different calculation. If it is unchoked, do a different calculation. But there is another important reason. If say you have found that it is choked, or if I have told you that it is a choked nozzle, still you need to find the pressure for performance calculation. How will you calculate the thrust in this case? What is the equation of thrust? Just don't have to tell the exact equation, but physically just tell me what constitutes the thrust. How can we calculate the thrust?
The rate of change of momentum of the gas.
Correct. So that can be calculated based on the change in velocity, inlet velocity minus exit velocity and mass flow rate. Okay, exit velocity we have calculated. But do we need the exit pressure also to calculate the thrust? You guys are not studying, huh?
Sir, like the kinetic energy is gained based on the pressure drop, right? So we need to know what the pressure drop is.
That is gained based on the pressure drop, but that is already related to temperature drop also. Everything is related, right? So because from the temperature directly we have calculated the velocity. For velocity calculation, we don't need the pressure drop. Okay, in this case. But pressure drop is still needed.
To calculate pressure.
We need to calculate the pressure thrust. Correct. There is a second term in the thrust. Okay, you guys have forgotten. Not studying. We are just please switch off your mic. There is another term which is the pressure thrust, which is only true if the exit pressure is different from the outside pressure. And in this case, the exit pressure is different from the outside pressure. Exit pressure is P5, outside pressure is PA. So P5 minus PA into exit area, nozzle exit area, should also give you some thrust. That thrust we need to calculate. Okay, that pressure thrust. So exit pressure also needs to be calculated. Anyway, we have digressed a lot. But
Sir,
what
you said that nozzle is unchoked. So
no, nozzle is choked.
Pressure should be PA only, right?
No, nozzle is choked. We are discussing now for nozzle choked. Unchoked condition we have discussed long time back. So all this we were discussing, that Suman or someone was telling, right? That gamma r T star, root over gamma r T star. These are all for choked condition.
Sir, so if you have an unchoked condition, then we don't need the exit pressure, right?
Correct. Exactly correct. If it is an unchoked condition, exit pressure and this P5 minus PA is 0. Pressure thrust is 0. Okay. You only need the momentum thrust. So already you have described for unchoked condition how to calculate the thrust. Now I was asking for choked condition how to calculate the thrust. And you guys were telling that like half of it was correct. That we can calculate the critical temperature by using this relation, and from critical temperature based on the relation of sound, speed of sound. Speed of sound is root over gamma at t star. So we can calculate the speed of sound, and at choked condition the velocity is equal to speed of sound. So speed of the velocity is also equal to root over gamma at t star. So my question was, because we can already calculate the velocity, what was the point in calculating the pressure? So the point is that for choked condition we also need to calculate the pressure thrust, that we cannot ignore. So that also needs to be calculated, and the pressure needs to be calculated. Now actually the difficulty comes. So this I was just trying to link so that you know how to connect your thought process. Means actually we will go step by step, but this type of thinking you should cultivate. Means you should generate how to connect the things together so that you can solve the problems. Otherwise you will find it very difficult to solve the problems. Okay. So once you read it, you just try to understand what is happening here. If you don't understand, again ask in the next class that I don't understand what is happening here. Because for all these types of jet engines, this is very important. So let me now formally go through this part. We will just go through this part. This is old material anyway. So convergent nozzle at unchoked condition, I think everyone is clear what to do. It is also discussed in the notes. So it is, if you are not clear, it is there in the notes. Gas turbine jet propulsion. Part 13, it is there for the nozzle treatment, how to calculate the exit velocity. Now let us come to the choked condition, what happens in the choked condition. Okay. So for the choked condition, when will the choked condition happen? If the pressure difference across the convergent nozzle is large, the nozzle will operate in choked condition. Okay. So by large I mean that it is greater than the critical pressure ratio. If the pressure ratio across the nozzle is greater than the critical pressure ratio, then the nozzle will performed in choked condition. Critical pressure ratio is around 1.7 something or 1.8 typically. You can calculate based on the gamma value. So that will give us the ratio of pressure beyond which there will be choked condition. Now if we want to increase the exhaust velocity beyond the sonic velocity, we cannot increase it using a convergent nozzle. Okay, we need to use a convergent divergent nozzle. If you use a convergent divergent nozzle, then you can keep on increasing the velocity indefinitely. Okay, if you just keep on increasing the divergent part. Convergent divergent nozzle looks like this, where this incoming velocity is subsonic, then the throat velocity is sonic, and then you on the diverging side, with increasing area, velocity keeps on increasing and it becomes supersonic. And if you increase the length of the, or increase the area of the diverging region, the velocity will keep on increasing. Okay, indefinitely it can be increased. So if we need very high velocity at the exit, we can use convergent divergent nozzle. But in practice, we don't use convergent divergent nozzle. Some comment is there? No. Because of practical difficulties. What is the practical difficulty? So in the nozzle, one of the practical aspects of a nozzle is that in jet engines, the mass flow rate is not constant. You cannot control the mass flow rate of air. Can someone say why we cannot control the mass flow rate of air in the jet engine as compared to, say, industrial gas turbine?
Speed have to be changed. Like
Speeds are changing, correct. At the takeoff, the speed is low. Yes?
Density also changes na, as per altitude is changing.
Density also changes, speed is changing. So conditions are changing, inlet conditions are changing, right? So mass flow rate is changing always. So if the mass flow rate changes, then for you guys, I don't know whether you have studied, because this is beyond the course content, this compressible flow. But the students who have done their power plant engineering class with me have at least studied about this part. Others who have not studied can take a look at the book of Chengel and Bose, thermodynamic book. one chapter is there on compressible flows. Okay, whatever we are discussing, some of these things are there. Okay, so for what was I telling here? Yes, mm, I have totally forgotten now.
Sir, you are saying that mass flow rate is not like it's
I have
uncontrollable.
had a long day. So from morning 7 o'clock I am working, so I got tired actually. So mass flow rate is changing, right? So at choked condition, velocity is equal to sonic velocity, right? So velocity is equal to sonic velocity. Now, if the velocity is equal to the sonic velocity here or here at the throat, this is the throat for the convergent nozzle, this is the throat for the convergent divergent nozzle. So if the mass flow rate is changing, how can you accommodate this different mass flow rate at the throat? Velocity is fixed, equal to the sonic velocity, and sonic velocity is also fixed. It is dependent only on the inlet condition, because inlet condition determines what is the stagnation temperature, and based on the stagnation temperature, this critical temperature here is fixed. Critical temperature here is fixed. Okay, it only depends on the gamma value. Okay, so because the critical temperature only depends on the inlet condition, this temperature here is fixed. So you cannot change the temperature. So the sonic velocity is fixed. So if the mass flow rate changes, if the inlet condition changes, obviously the sonic velocity will change, but it will not change according to the mass flow rate. Okay, because mass flow rate also depends on the inlet velocity, density, things like that. So it will not change according to the T star. So how to accommodate this change in mass flow rate? What is the option to us, to the engineers, to accommodate this mass flow rate? Because you know that at choked condition we cannot increase the mass flow rate, right? Is it known to everyone that in choked condition, in a nozzle or in a converging nozzle or in a converging diverging nozzle, we cannot increase the mass flow rate? Or is there any confusion? We cannot increase the mass flow rate. Okay, mass flow rate is fixed in choked condition. That is why it is called choked. Otherwise, this term choked will not have come. So the only option that is left to us to increase the mass flow rate is to increase the area. Okay, because velocity is fixed. Velocity is fixed, density is also fixed at that point. Temperature is fixed, density is fixed, T star, rho star, everything is fixed. Only option left is to change the area of the throat. So it means that you have to design the engine with variable throat, design the nozzle with variable throat area. Okay, it is a difficult task. So for a convergent divergent nozzle, it is a very difficult task. But for a convergent nozzle, it is not so difficult, relatively speaking. You can have overlapping flaps, and by changing the overlap, you can change the converging area. Let me check whether we can have a Google image or something. For a or let me see whether we have here itself. Okay. I think for a jet aircraft, you will be able to notice if we have an afterburner. No, it does not have this. This from this picture, it is not clear. MiG-21 nozzle. Okay. This is a very old engine, but still it has some mechanism. MiG-21 is there in our lobby. That is what I was saying, right? We have one. So actually the throat area can be changed. It is designed in such a way, either by overlapping. This case is because this is old design, it has a somewhat different mechanism of changing the throat area. The newer engines, Like some mechanism will be there to change the throat area. Okay, some mechanism will be there. And that is much easier for a convergent nozzle as compared to convergent divergent nozzle. That's why even for supersonic aircrafts also, although convergent divergent nozzle would have been ideal, means would have given the highest velocity, exhaust velocity. Why it would have given the highest exhaust velocity, convergent divergent nozzle? Because we could have expanded the gas from this 0.04 to totally to 0.5. Okay, we could have expanded the gas from 0.4 to 0.5. We would not have stopped at the critical point, because in the divergent part we could have expanded up to 0.5. So we would have, because the change of enthalpy would have been higher, the exhaust gas velocity would have been higher, supersonic velocity, higher than the speed of sound. Okay, but we do not use convergent divergent nozzle because of these design limitations. Okay, it's very difficult to design. Only in specific cases where it is means it is so much required that then only we will use. Means, for example, if the velocity is too high, say for a scramjet engine or rocket, so you will see that for rockets we have a convergent divergent nozzle. Okay, so otherwise we use convergent nozzle. Even for military aircrafts which fly at 2 times the speed of sound, the nozzle is only convergent. So this MiG-21 that I was showing, these are supersonic aircrafts, right? This can go supersonic while using afterburner, but still has only this type of convergent nozzle. But if you take a look at say space shuttle nozzle, let me see space shuttle nozzle some, because in this case the velocity needs to be very high. So this is the space shuttle nozzle. Okay, now you can see the difference as compared to the aircraft nozzle. This is diverging, right? So actually there is a converging part also, it is not visible inside. So there is the throat somewhere around here, and this is the diverging part of the nozzle. So actually this is not a diffuser, this is the nozzle, and this is accelerating the exhaust gases to very large supersonic velocity. And that is needed because you need your space shuttle to go at very high velocity. Means Mach 20, Mach 30 velocity actually is attained. So that type of velocity cannot be obtained obviously using normal. In that case, it is justified to use the high cost and variable throat area and everything whatever is needed. In that case, variable throat area is also not needed because there the oxidizer rate can be controlled. Mass flow rate can be controlled for rockets, but for jet engines it is tricky part. Again, I have digressed, but my main point in this discussion was that to say that from practical point of view, convergent divergent nozzle is difficult to use. So even for supersonic aircrafts, convergent nozzles are used. So when we use convergent nozzles, the main advantage is that the throat area can be changed to accommodate variable mass flow rate. However, for convergent nozzle, if the pressure difference is too high, the nozzle becomes choked. And in that case, you cannot fully utilize the pressure difference to expand the gases. So your thrust, momentum thrust is lower as compared to convergent divergent nozzle. However, some of the loss can be recovered by using, because we can generate some pressure thrust. Because some pressure thrust is generated, we can recover some pressure thrust. Okay. So this is already there in the notes, whatever we have discussed. So one important point you should note here, sometimes again students get confused. Okay. Again, I will ask the question without showing that part. The maximum, what is the maximum velocity in the convergent nozzle? What is the maximum velocity of the exhaust gases that can be attained using a convergent nozzle?
The critical velocity.
Critical velocity, which is what? Sound, speed of sound, right? What do we mean by critical velocity?
Yeah, speed of sound.
Speed of sound, right? So then the question, my question is, if the maximum exhaust gas velocity is equal to speed of sound, how can we accelerate supersonic aircraft using convergent nozzles, which is flying at higher speed than speed of sound? Why is the flaw in my question?
Like repeat the question once.
My question is that maximum exhaust gas velocity, you are saying that the maximum exhaust gas velocity that can be obtained using a conversion nozzle is equal to the speed of sound. Now I am saying that conversion nozzles are also used for supersonic aircrafts. Now if the for the supersonic aircraft, if the maximum exhaust gas velocity itself is sonic velocity, how can the aircraft fly at supersonic speed? Where is the flaw in my logic? Because
Sir,
to
like
generate
the
thrust,
speed
yes,
of sound is root gamma RT, right? So it changes with
yes,
temperature.
correct, correct. This should be clear to others. This is a very good point, very good answer. But other students get confused every time. So when we say supersonic aircraft, generally we are saying it as supersonic as respect to the ambient temperature, right? So ambient temperature maybe say 220 degree Kelvin, 220 Kelvin, or maybe maximum 250 Kelvin, 280 Kelvin, or whatever. Okay, less than 300 Kelvin or 300 Kelvin. So the ambient speed of sound is gamma into R into 300 root over that. Now the exhaust gas temperature is much higher. Correct. We can see even from this diagram also that the exhaust gas temperature is much higher than the ambient temperature. T5 is much higher than TA. So it means that at the exit condition of the nozzle, the sonic speed is much higher than the sonic speed in the ambient condition. So although the exhaust gas is at sonic speed, it is actually at a much higher velocity as compared to the aircraft velocity. Although the aircraft is flying supersonically, mean the exhaust gas velocity may be 600 meter per second and the aircraft may be flying at 500 meter per second. Still the aircraft is supersonic because the sonic velocity is only 340 meter per second at ambient condition. Is it clear to everyone my point? Because this point actually
Yes,
many
sir. Yes.
students get confused. This is a very important point.
Density
Okay,
is different, no? So
not only density, temperature. The main thing is the temperature is different. Okay,
temperature actually change the density, na density, na so.
so what?
Okay.
Velocity depends on the gamma RT. No, density does not come into picture. Okay. If you are saying that master rate will change, master rate cannot change. Master rate will change obviously at different altitude, but master rate cannot change at the means inlet master rate should be equal to the exit master rate. Okay. So temperature is the critical factor. So because high temperature is present at the nozzle exit velocity, at the nozzle exit condition, the speed of sound is also higher. So if I take a look at this convergent nozzle, where is the speed of sound lowest and where is the speed of sound highest?
Lesser at inlet, higher at outlet.
Speed of sound is lesser at inlet and higher at outlet. Why is
Since temperatures are increasing.
this correct? What others are saying? Other
Like
students.
it should be the reverse, sir. Temperature is decreasing in the nozzle.
Correct. Temperature is decreasing in the nozzle, right? So stagnation. So speed of sound is highest at the inlet because temperature is highest at the inlet. Because otherwise, if temperature is not decreasing, how will the velocity increase? Stagnation temperature remains constant.
Yes,
So velocity
I confused.
velocity increases means static temperature is decreasing, right? So static temperature is highest at the inlet, so speed of sound is highest at the inlet. Speed of sound actually decreasing in the nozzle. You are thinking about the case what I was saying, ambient temperature, inlet temperature is low, but nozzle inlet temperature is high. So nozzle inlet temperature is equal to the turbine outlet temperature. It is high. So actually speed of sound is even higher at the nozzle inlet. Okay. So just I am trying to open up your thought process. That is the thing. So let us take a break and then we will continue this discussion. We will go into some mathematical details. Okay. So 5 minutes break. Meanwhile, you can take a look and try to understand these diagrams, whether you can understand these diagrams, because this is what we are going to discuss after this break. Hello, can you hear me? Hello.
Yes, sir.
Okay,
Yes, sir.
so for convergent nozzle with choked condition, we want to find out the exit conditions for a given efficiency, means not isentropic nozzle. Isentropic nozzle is easy to find. Non-isentropic case we want to find. Okay, so let us, before going into this non-isentropic case, let us once see how to find for the isentropic case. Okay, this you should be able to do based on the total discussion or whatever discussion is there. So how will this TS diagram look like for a isentropic nozzle? This is not there in the notes because we will be considering actual cases, but let me just show you. So this is the nozzle inlet pressure. I am going to call it as P04, and this is the nozzle exit pressure line. I am going to call it as P5. Okay. This is a choked condition, so ambient pressure is somewhere around here, PA. Okay. So choked condition, P5 is greater than PA. Okay. So if it is an isentropic nozzle, it means that we are just going straight down, right? Entropy is constant, no losses. And you are going from this point 0, 4 to 5. So I want to find out P5. Okay, so what should be P5? Let us again revisit the steps once to summarize everything. T04 is known to us, and for isentropic or adiabatic nozzle, T05 is equal to T04. Okay, so the T05.05 point is also here, same point, coinciding. Okay, coinciding with this same point, and T05 by T5 is equal to gamma plus 1 by 2, because that is the relation, because T5 is equal to T star. Basically, T05 by T star is equal to gamma plus 1 by 2. From the equation, you can check the equation in the diffuser part. We have discussed already, and it is very easy to derive. I have shown how to derive based on CP and gamma RT, all these relations from fundamentals. You don't have to go to any books also. So because T5 is equal to T star, we can write T05 by T5 equal to gamma plus 1 by 2. Then P05 by P5 is equal to T05 by T5 to the power gamma plus gamma minus, sorry, gamma by gamma minus 1. This is clear to everyone? How to calculate P5? P5 is equal to P star. Okay, choked condition. So P star is the choked pressure, critical pressure, as we were seeing. So this is nothing but P05 by P star is equal to gamma plus 1 by 2 to the power gamma by gamma minus 1. Okay. So not difficult to understand. Is there any doubt here? Please let me know, because otherwise you will not be able to understand the next part. So I am hoping that if I give a problem in the exam for this case, everybody will be able to solve. Okay. P05 by P5. So what happens in a non-isentropic case? Now that is the question. Okay. Isentropic case, nothing difficult to understand. So what do you think should happen in the non-isentropic case? How will the process go? Non-isentropic means entropy can only increase, right? So it should go something like this. Correct? Or is there any confusion?
Yes, correct, sir.
Okay. So what should be the critical temperature at the exit? It should be still equal, right? Because it's adiabatic. Although it is non-isentropic, it's still adiabatic nozzle. Okay. So actually what is going to happen is the tricky part. Everybody means one of the most tricky part of this course. Everybody gets confused. So let me just make you understand this part. Okay, this diagram is not accurate. Let me draw in an exaggerated way. So the temperature 0.5 is equal to 0.4. Okay, it is the same temperature, but it is at a different location because entropy has increased. The 0.5, okay, the actual 0.5 as compared to now, let us call this as 5s because this was the isentropic case. So at the choked condition, can the temperature change whether it is isentropic or non-isentropic?
No, sir, it will be the same. Like similar to
It
the
is the same. It
diffuser,
just
what
follows.
we have seen.
It is the same equation, right? Whatever is the means, if it is an adiabatic nozzle, all the nozzles are adiabatic, whether it is isentropic or not. So T05 by T star has to be gamma plus 1 by 2. Okay. So this is always going to be the same. So this T star is always going to be the same. Correct. Whether it is a isentropic case or non-isentropic case. But the constant pressure line through the isentropic case goes like this. So what should be the constant pressure line through the actual case? Let me take another color. Constant pressure line through the actual case, because the temperatures are same point, so the constant pressure line will be lower, right, as compared to the isentropic case. So if this P star isentropic case, the P star is this one. For the actual case, the choke pressure will be lower than this value. Is it clear to everyone? Although the temperature is same, whether it is isentropic or not, the pressure at the exit of the nozzle is lower as compared to the isentropic pressure for a non-isentropic nozzle. Is it clear from the diagram? Because the constant pressure line is, you are connecting to a lower constant pressure line. Physically, you can understand as there is, because of frictional losses in a non-isentropic case, there is some pressure drop. Okay. Although this does not reduce the temperature because the frictional losses manifest as temperature itself, but this actually reduces the pressure somewhat. So to achieve the same velocity, the pressure actually is, the pressure difference is higher to achieve the same velocity. Okay. So this is the important point. This is actually mentioned here. So I will this diagram now it looks. So there is a, so you should not get confused here. Okay, one confusion is there. This 5s point is not the same as this 5s. Okay, what I have drawn here. Okay, so this was I was describing, so I have drawn this 5s. What I have drawn is this point there. Okay, corresponding to the, so I will just show you in a bigger format so that everyone is clear about this. Forget this case. This case we have already described. Okay, so I am showing two cases. One is case 1, where the pressure at the exit is less than the, means is greater than the critical pressure. The pressure ratio is less than the critical pressure ratio. We have already discussed this point too many times, that in this case P5 is equal to PA, and you can always calculate what is the velocity. Okay, velocity is equal to 2 into Cp into T04 minus T5. This is valid for unchoked nozzle. This we have discussed multiple times. How to calculate T5s from T04 to T5s based on pressure ratio. Pressure you can calculate based on ambient pressure, and based on nozzle efficiency you can calculate T5, and velocity you can calculate. Okay. So what we are interested is in the second type, the choked condition. Okay, so same diagram I have drawn again here for the choked condition. What happens in the choked condition? This instead of going like this, the process follows a path like this. Okay, so if we had followed an isentropic path, what would have been the temperature at the exit of the nozzle for an isentropic nozzle? The temperature would have been equal to T5.
T5.
Okay, T5, because temperature remains same that we have discussed. So temperature would have been equal to this green line, where the green line intersects the pink line. Okay, so the pressure, critical pressure PC for isentropic flow would have been this green line. Okay, that is what I was showing here by this red line. Okay, so this green line would have been the critical pressure, and our nozzle process would have gone from 04 to this point. But because of non-isentropic nature of the nozzle, because of frictional losses, we are increasing the entropy. The total temperature remains same, stagnation temperature remains same. So T04 equal to T05, and what has happened is that the static temperature is equal to the static temperature that we would have obtained if it was an isentropic case. Okay, so this T star, which is given by T05 by T5, is equal to gamma plus 1 by 2. Okay, so this point also is known. So the constant pressure line through this point is the critical pressure for the actual flow. The critical pressure for the actual flow is different from the critical pressure for the isentropic flow. Okay, so if you directly calculate the critical pressure from the isentropic flow from this relation, this is only valid for the isentropic flow. This is not valid for our this new actual flow. Although the temperature is valid for all cases, the pressure is not valid because of pressure losses. Okay, so this equation is only valid for the isentropic case. Okay, so this will give you the PC value for the isentropic flow. PC for actual case is actually lower than the isentropic case. So we need to find that PC, and that actually depends on the nozzle efficiency. So how to find that? So if we extend this line for the isentropic case so that it intersects the actual pressure line, and say this point we define as P5S. Okay, 5S. This is the isentropic temperature corresponding to the actual pressure. Okay, this is not the exit point for the isentropic nozzle. This you have to be very careful. I will repeat again. It is also there in the video recording. It will be there. You just listen to it again if you are confused. For an isentropic nozzle, the exit point would have been where my mouse cursor is. The intersection between the green line and the pink line, red line. Okay. However, if we extend this line so that it goes to the actual pressure line, how do we know what is the actual pressure line? The actual pressure line is equal to the pressure line which goes through the actual temperature corresponding to this entropy. Okay, increase in entropy. So if we continue this, and wherever this line intersects, if you denote this point as 5S, this is a hypothetical point 5S. Okay, based on this, we are going to define the nozzle efficiency. So the nozzle efficiency is defined as T04 minus T5S. So sorry, T04 minus T5 by T04 minus T5S. Okay. So now let us go through the steps for this problem. Okay. So you know the inlet condition of the nozzle. Inlet condition is equal to T04 and P04. Both are known from the calculation of the turbine. We want to find out the
Sir, you are not audible.
Sir.
I dropped off. Can you hear me now? Internet connection got dropped off.
Yes, sir.
At what point did it drop off? Towards the end of the discussion, huh?
Yes, going with the ongoing calculation after that. You efficiency
On
part you described.
efficiency part I have described. So I was saying that how to calculate the thrust, right? These things we have discussed. You have heard momentum thrust plus pressure thrust.
No, sir.
Oh, you missed all this part, huh? Okay. So what I am saying is that, so for a choked condition, ultimately for any condition, our aim is to find out what is the, anyway we will do a problem also in the next class, but what is the thrust and how to find the thrust for a choked condition. It will be a summation of the momentum thrust and the pressure thrust. Okay. So what will be the steps for a choked condition nozzle to find the thrust? First we will try to find the momentum thrust, right? Can you hear me?
Yes, sir. Yes.
Yes, sir.
Okay.
Yes, sir.
So first we will try to find the momentum thrust. So mass flow rate is already known to us. Fuel air ratio we have already calculated based on the combustion chamber process. Vi is already known to us. So only unknown is Ve. So how to calculate Ve for choked condition? V is nothing but equal to the exit velocity from the nozzle, right? So it is equal to V5. At choked condition, this is equal to the sonic speed at temperature T5. So V5 is equal to root over gamma at T5. So is the sequence clear up to this point to everyone? Velocity at this
Yes,
point.
sir. Yes, sir.
Okay.
Yes, sir.
So next point is how to find T5. Okay. So for calculating T, I will come to this whatever is written. For calculating T5, so T04 is equal to T05. That is not going to whatever we have discussed. Isentropic adiabatic case, stagnation temperature remains constant. So T04 by T5 is equal to T05 by T5 is equal to 1 plus gamma g minus 1 by 2 into m5 square. Okay, this is the general relation. M5 in this case is equal to 1. Mach number is 1. So you replace 1, you get gamma g plus 1 by 2. So T05 by T5 is gamma g plus 1 by 2. T05 we can already calculate because we know what is T04. So T05 equal to T04 and gamma g plus 1 by 2 is already known. So we can calculate what is T5. Okay. So because we can calculate T5, we can calculate the velocity V5. So this velocity V5 is equal to V. Okay, we can replace, we can find the momentum thrust. So up to this point, it will be clear to everyone how to find the momentum thrust for choked condition. Is it clear?
Yes, sir.
Yes.
Okay. This same thing is written here, so don't worry about it. Whatever I have explained, critical temperature ratio is same for isentropic and irreversible adiabatic flow because stagnation temperature does not change. So same thing is there. We have already discussed this. So critical temperature is 2 by gamma g plus 1 T04. So up to this point we have discussed already. Okay. So the question is how to find the pressure thrust. Okay, temperature, the momentum thrust we have already calculated. So to find the pressure thrust, we need to calculate what is PE, which is the pressure P5. We need to calculate the exit pressure. Okay, and we cannot use the adiabatic relation, isentropic relation that P05 by P5 is equal to T05 by T5 to the power gamma by gamma minus 1. Okay, that we cannot use because this process is not isentropic. Okay. So we have to find the isentropic point 5s and then we will use the relation between 0,4 and 5s. So to find the isentropic point 5s, so I will keep this open here now. The same diagram that we are considering. Okay. So efficiency of the nozzle is defined as T04 minus T5 by T04 minus T5s. It is always less than 1, less than equal to 1. So from this you can calculate what is T5s because T04 is known to you and T5 is we have already calculated. Okay. Because T5 is the critical temperature. So based on this we can find out what is T5s. If you want to write in expression form, it is this form, or we can numerically directly calculate T5s. So once T5s is calculated, you can find out P5, which is equal to P5s. So P5 by P04 for this isentropic process is equal to T5s by T04 to the power gamma g by gamma g minus 1. Okay. So this is the this will give us the exit pressure. Okay. If you want to write in the form of expression, we can write like this. So eta n is equal to T04 minus T5 by T04 minus T5s, from where we can write T04 minus T5s as, just taking this to the other side, is equal to 1 by eta n T04 minus T5. Okay. And we can write T5s as T04 minus, so same thing, T5s you take to the other side and this expression you take to this side. So T5s is equal to T04 minus 1 by eta n T04 minus T5. All these parameters are known. Okay, T5s is the unknown. So now in this expression you replace T5s. So P5 by P04 is equal to T04 minus 1 by eta n T04 minus T5 by T04. Okay. So ultimately it gives us P5 is equal to P04 into this T04 by T04 gives us 1 minus 1 by eta. Then T04 by T04 here also gives us 1 minus T5 by T04. T5 is the critical temperature. So you can either write T5 or T05. This to the power, entire thing to the power gamma g by gamma g minus 1. Because we know that critical temperature by T04 is equal to 2 by gamma g plus 1. You can replace this here in this expression and simplify it to get the critical pressure for the actual condition, not for the isentropic condition. So for the actual condition, this is the expression for the critical pressure. It also has the expression of the nozzle efficiency. So it is equal to P04 1 minus eta n gamma g minus 1 by gamma g plus 1 to the power gamma g by gamma g minus 1. Okay, somewhat complicated expression. You don't need to memorize it. You can derive it, or while solving the problem, you can just proceed step by step. You don't have to find the expression form. This is true for the choked condition for non-isentropic nozzle, for actual nozzle. Okay. If the nozzle efficiency becomes equal to 1, eta n will become equal to 1. So your expression will become 1 minus nozzle efficiency 1 means what physically?
The temperature.
It's what type of nozzle is it? Nozzle efficiency 1 is process is isentropic, right?
Yes, sir.
Efficiency 1 means isentropic process. Correct. Means 5 and 5s coincides. So nozzle efficiency equal to 1 means if you put here for the isentropic process, this becomes equal to 1 minus 1 by 1. So 1 minus gamma g minus 1 by gamma g plus 1. So you take it to the other side, gamma g plus 1 minus gamma g plus 1. So you will be left with 2 by gamma g plus 1. Correct. So this is the same as this expression. It is the opposite way I have written P5 by P04. So here it is the P05 by P star. So it is 2 by gamma g plus 1 to the power gamma by gamma g minus 1. Same expression. This expression will become equal to this expression if you replace eta n equal to 1. This is one way to verify that we have correctly obtained the equation. So once you have the pressure, how to calculate the pressure thrust? We want to calculate the pressure. So P we have obtained, PA we have obtained. The only that is the exit. Okay, so if mass flow rate is known to us, we can calculate the exit area of the nozzle. Exit area is the mass flow rate at this point. So if it is if you want to calculate accurately, you have to also consider the fuel air ratio, m dot I into 1 plus f. If you ignore the fuel air ratio, this is just m dot. Okay, so whatever is the mass flow rate divided by, so the exit density into exit velocity means m dot is equal to rho av, right? M dot is equal to area into density into velocity. So area is equal to mass flow rate by density into velocity. So density at this point is the critical density, because we have already calculated the critical pressure at this point Pc. This is the actual critical pressure, this critical pressure P5. So this is P5 by RT5 is the density rho 5. Okay, you don't have to again go through equation, you can just calculate based on ideal gas law P5 by RT5. All these calculations are for ideal gas law. Okay, and V5 we have already calculated, it is equal to gamma g into RT5. Okay, so if you put these two things here, you will get what is the area A5. So then you can calculate PE minus PA into A5, which will give you the pressure thrust. Okay, so in the next class we will solve a problem, general problem on turbojet engine step by step, and then we will move on to the turbofan engine. Okay, so all the steps we will see for turbojet. But before that, you can just check once. This is not actually a problem. This is just a two-line problem. Just to get your understanding clear, you can try this. Okay, I don't know the answer also. Say PA is equal to atmospheric pressure is 0.2 atmosphere, and using the same terminology that I have given here. Okay, P04 is 1.2 atmosphere at the inlet of the nozzle. T04 is 800 Kelvin at the inlet of the nozzle. Ambient temperature is 230 Kelvin. Okay, ambient pressure is 0.2 atmosphere, ambient temperature is 230 Kelvin. Nozzle efficiency, find out what should be the, step by step proceed. Don't put in the formula. Step by step proceed and find out what is the nozzle exit pressure. Okay, this is just a 2-3 line problem, just to clear your understanding. In the next class, we will actually solve a proper problem on turbojet engine. So we'll stop here. I will take the attendance. Go through these notes again so that you are clear in the next class. This part is very critical, very tricky to understand. Otherwise, you will make mistake in the exam. Okay, this part everybody confuses each year. This part is very tricky to understand. That for an isentropic and non-isentropic nozzle, the key understanding point here is that for an isentropic and non-isentropic nozzle, the critical temperature remains same, but the critical pressure does not. The pressure is actually lower for a non-isentropic nozzle. And if you keep on making the nozzle with lower and lower efficiency, means if the losses are more and more, critical pressure will become lower and lower. Okay, this is the most important thing. Then everything other things will, and once you know you can draw the TS diagram correctly, everything will fall into place. So tomorrow again, no, not tomorrow, when the next one, Wednesday again, we have a class. So Wednesday we will solve a problem and then move on to some characteristics of turbojet engine. like how the performance changes. Some MATLAB plots I can show you for the turbojet part, and problem itself may take 1 hour long problem because it will have lot of steps, and then we will go to turbofan.
Sir, that nozzle efficiency, why can't we define it in terms of pressure differences?
It can be defined in terms of pressure differences, but generally this type of efficiencies, these isentropic efficiencies are defined in terms similar to, say, for the diffuser like we had defined. Okay. But it can be defined. So you can define another efficiency. It will not be called as isentropic efficiency. You can call it some other efficiency, but it can be defined in terms of this pressure, like some function of this pressure PC for isentropic, say PC by P04, or like PC minus P04 minus PC by P04 minus this PC, something like that you can define, so that the value is less than 1 or something like this. Okay, it can be defined, but as a convention, all isentropic efficiencies are defined in terms of temperatures. Okay, but the other type of efficiency you can define. Good question. But who is there here? Bharatram is there. Then yes, I can see your name. Sachin Kumar, Sachin, not present.
Sir, I'm present, sir. My mic got mute. Present.
You just raise the hand beforehand, okay? Before your name
Okay.
comes, 2-3 names, because there is some lag. It takes some time to register for me.
Sir, did it?
So,
Yeah,
okay, you are present. Yes, Sanjay is present. Then Abhishek Anand is present. Vikas is present.
Present.
Manthan is present. Ajay Kumar Meena is present. Then Gaurav Kandalwal. Gaurav, where are you, Gaurav? Gaurav is not present. Then Jishnu is present.
Gaurav is present, sir.
Oh, Gaurav is present. Where are you? Where is your name? Yeah, it is there. Okay, correct. Thank you. Jishnu is present. Suresh is present. Ujjwal is present. Shubham Kumar is present. Pushpendu is present. Amgod Shyam Kumar is present. Prabhat Kumar Mishra is present. Kishan Sai is present. Dhruv is already left. Dhruv is not here. Then Venkata Rajendra is present. Then Atul is present. Ramcharan is present. Suman was present. Yes, Suman is present. Ashwini Kumar is present. Gaurav Srivastav, I think I saw Gaurav Srivastav. Where is he? Gaurav Srivastav? I don't see here. Not present. Then Gulshan Kumar is present. M. Pujari present. Nilesh Kumar present. Chintu present. Sudipto present. Then Lokesh I think so. Yes, present. Ankit has left, right? Ankit also has left. Shivangsh is present. Gaurav, not Khandelwal. Gaurav Khandelwal is present. Gaurav Srivastav is not present. Okay, everyone else is present. We'll meet on. So unfortunately, most probably we will have to continue the extra classes on Monday. I know it is difficult for you guys, but I want to complete the syllabus. Let us see. Most probably next Monday also we will have extra class. I will let you know. Okay. Other option is that I don't solve any problem in the class, but that will not be the ideal situation. So better that I solve some problems in the class, and we continue also on Mondays. So we will stop here. Please